We are in Chapter 11, Infinite Sequences and Series, Part 2. Section 11.7 is Strategies for Testing Series. In this section, we look at all the different tests that we've been introduced to throughout this chapter, and we're going to talk about different strategies in order to determine which testing strategy to use. So first thing is to classify the series according to its form. So don't forget that the sum of 1 over n to the p is a p-series. And a p-series is going to be convergent if p is greater than 1 and divergent if p is less than or equal to 1. The next thing is to consider a geometric series. So if it has the form of the sum of a times r to the n minus 1 or a times r to the nth, that's going to be called a geometric series. And it's convergent if the absolute value of r is less than 1 and divergent if the absolute value of r is greater than or equal to 1. If the series has a form that is similar to a p-series or a geometric series, then one of the comparison tests could be considered. So if a sub n is a rational function or algebraic function of n involving roots of polynomials, then the series should be compared with a p-series test. Comparison test only applies to series with positive terms. So if the sum of a sub n has some negative terms, then apply the comparison test of the sum of the absolute value of a sub n and test for absolute convergence. 4 says if you can see the limit as n approaches infinity of a sub n does not equal 0, then use the test for divergent. And 5 says if the sum of negative 1 to the n minus 1 times b sub n or the sum of negative 1 to the n times b sub n, then you're going to use the alternating series test. 6 says the series that involves factorials or other products including constants raised to the nth power, use the ratio test. And if a sub n is of the form of b sub n to the nth power, then use the root test since it's raised to that nth root. And the last one says if a sub n equals f of n, where the integral from 1 to infinity of f of x dx is easily evaluated, then the integral test is effective. So a lot of times there's multiple ways to go about to deal with these, so make sure you show clear steps and clear work, and then also don't forget you always need to state which test it is that you used to solve this, to figure out if it was convergent or divergent. The example right below says test the series for convergence or divergence. Again, make sure to state which test it is that you used. So for part A, it's the sum from n equals 1 to infinity of 2n plus 1 raised to the nth power and n raised to the 2nth power. So right away I notice that both of these have an exponent with n, and so my mind goes directly to the root test. And so in order to use that root test, if you don't remember that was in the last section, make sure to pause the video and go back and look at that last section, which was 11.6. And for the root test, we're going to look at the absolute value of a sub n, which is going to be the absolute value of, and we have 2n plus 1 to the nth power and n to the 2n. And I'm going to go ahead and pull that nth power out. So I have 2n plus 1 over n squared, all raised to the nth power. And again, taking that absolute value. So then we have the limit as n approaches infinity of the nth root of the absolute value of a sub n, which is going to be the limit as n approaches infinity of the nth root of the absolute value of 2n plus 1 over n squared, all raised to the nth power, which is going to equal the limit as n approaches infinity of 2n plus 1 all over n squared. Evaluating this limit, we get infinity over infinity, which is indeterminate. So I'm going to multiply both the top and the bottom by 1 over n to the second, which is that degree in the denominator. And this will allow me to rewrite this limit as n approaches infinity of, it's going to be 2 over n plus 1 over n squared, all over 1. And as we do this, you'll notice that both terms in the numerator would converge to 0. And so this is going to equal 0. And since 0 is less than 1, and this is our L value, is less than 1, we can say that it is absolutely convergent. So therefore, the sum, the original one that we had, which is from n equals 1 to infinity of 2n plus 1 raised to the nth power over n to the 2n, is absolutely convergent. And this is by the root test. So we can say, therefore, it is convergent. B says the sum from n equals 1 to infinity of negative 1 to the nth power times n over n squared plus 2. I notice that this is alternating, so I'm going to consider the alternating series test. And to do that, I'm going to look at b sub n, which is going to be just n over n squared plus 2, which is going to be greater than 0 for all n. And again, we're only dealing with n that are going to be greater than or equal to 1. And in order to do the alternating series test, we need to make sure that it is decreasing. So this is not as clear that it is decreasing. A couple things to note is, one, you could take the derivative of this using the quotient rule to show that it is decreasing. Another thing to note is that the degree in denominator is increasing quicker or faster than numerator. So therefore we can say that this is a decreasing function. So our terms are decreasing. The second thing that we needed to show was looking at the limit as n approaches infinity. And this needs to equal 0. And so we have n over n squared plus 2. And again, evaluating this limit, it is indeterminate. You'd have infinity over infinity. So multiply both the numerator and denominator by 1 over the degree of the denominator, which is 1 over n squared. So we have the limit as n approaches infinity of 1 over n over 1 plus 2 over n squared. And again, remember, as you take that limit, both 1 over n and 2 over n squared would both converge to 0. And so this is going to be equal to 0 over 1, or just 0, which is the second thing that we needed to show. And so therefore, since both those terms are held true, it's decreasing, and it also the limit is equal to 0. And also that all of our b sub n terms are positive. They're all greater than 0 for all n greater than or equal to 1. We can say that the original series that we had converges by that alternating series test. So the sum from n equals 1 to infinity of negative 1 to the nth power times n over n squared plus 2 converges by the alternating series test. We have 4 more of these on the next page, and I'm going to go ahead and circle all 4 of these. This is actually going to be how we start class, and I will have you guys work on these together in groups and discussing which method to use and determining if they converge or if they diverge. So make sure you come to class prepared and you understand all these different tests. Maybe outline them on a piece of paper. We have 2 more that we'll work on together right now. So the next one that we have is G, and G says the sum from n equals 1 to infinity of sine of 2n over 1 plus 2 to the nth. And with this one, I noticed that it's not very nice. It would definitely not be nice to integrate, so definitely not the integral test. It's not alternating. It's not going to be using a root because not everything has that nth root on it. So usually when they're like this form, where it's maybe a little bit different of a problem, where it's not so easy to see, it's a little bit more, we have a trig, we have a polynomial, we have an exponential, we have all these different things going on to it, I'm going to consider the comparison test. And remember, we also have the limit comparison test. But I'm going to first consider this comparison test. And I'm going to compare this, since I know that sine of 2n, I'm going to write down up here, sine of 2n is in that interval from -1 to 1. And so if we let a sub n equal the original function, which is sine of 2n, over 1 plus 2 to the nth, and compare this to b sub n, and I'm just going to say that b sub n is going to be equal to 1 over 1 plus 2 to the nth. We can say that this is going to be, since sine, the max value that sine has is 1, this would be less than or equal to b sub n. And you can even simplify b sub n a little bit more and say this is less than or equal to, if I got rid of the 1 in the denominator, I can say that that is even smaller than just 1 over 2 to the nth power, which you can rewrite as 1 over 2 to the nth power, which we know is a geometric series. And so we can say b sub n, the sum from n equals 1 to infinity of b sub n, which is 1 over 2 to the nth power, converges because by the geometric series test. And this is because r is equal to 1/2. And remember that if the absolute value of r was less than 1, then it converged. And so since b sub n converges, so b sub n converges, and a sub n is less than or equal to b sub n, we can use the comparison test, and that says that therefore the sum from n equals 1 to infinity of sine of 2n over 1 plus 2 to the nth power converges also. And this is by the comparison test. So the next one, h, says the sum from n equals 1 to infinity of n to the second plus 1 over n to the third plus 1. And I noticed that if I were to use the comparison test like I did in the last one and get rid of some of those 1's, the 1 in the numerator and denominator, I would be left over with n squared over n cubed, or 1 over n, which is perfect. However, eliminating a 1 in the numerator and a 1 in the denominator isn't going to do much to being able to compare it to something. But I also remember that I had the limit comparison test. So again, go back and look at the limit comparison test really quick before we try this example. And the limit comparison test was you had to define a sub n, which is n squared plus 1 over n cubed plus 1, and b sub n, which again, you don't have to compare it in terms of a mathematical symbol in here, but b sub n, I would get rid of those 1's and say n squared over n cubed, or just 1 over n. And so the limit as n approaches infinity, and the limit comparison test is going to be of a sub n over b sub n, which is n squared plus 1 over n cubed plus 1, all over 1 over n, which if you multiply by that reciprocal of the denominator, this is going to simplify to the limit as n approaches infinity of, and we have n cubed plus n all over n cubed plus 1. And evaluating this, we get infinity over infinity, which is indeterminate. So again, we're going to multiply by the degree in the denominator, 1 over that. So 1 over n to the third to everything in the numerator and everything in the denominator. And so we have the limit as n approaches infinity of 1 plus 1 over n squared over 1 plus 1 over n cubed. And as you take the limit as n approaches infinity, 1 over n squared and 1 over n cubed are both going to converge to 0. And so this is going to simplify to just being 1 when you evaluate this, which is greater than 0. And we know that b sub n, which is going to be the sum from n equals 1 to infinity of b sub n, which is equal to the sum from n equals 1 to infinity of 1 over n, diverges because it's a harmonic series. So it's a harmonic series. And so we can say that therefore the series that we had, which is n equals 1 to infinity of n squared plus 1 over n cubed plus 1, diverges also. And this is by, make sure to state what test you use, by the limit comparison test.